Hello everyone, today we will be looking at the calculation of Ecell value. So we will be using the standard electrode or the standard reduction potential. So I would like to show you the E values, so-called the standard electrode potential, SEP or SRP. Okay, so you can see here. So E values, SEP, SRP, they refer to the same thing. All right. Now, whatever you're looking at is the 2022 to 2024 version. So 2022 and 2024, the 3-year syllabus, the E values are provided in the question paper itself. So you will not be provided with another data booklet like the previous syllabus year. Okay, but I want to show you for 2022 to 2024, you can obtain these few sheets of document in the syllabus. All right, so what I've done is I extracted out, and you can see they are arranged in alphabetical order over here. All right, and you can see this is how it looks like it. Okay, like this. All right, so it's from page 78 to page 79. But most of the time, I would prefer to use the 2019 to 2021. Okay, as you can see over here. Now, this one also shows the same standard electrode potential. But then they will provide you in A, alphabetical order, in B, decreasing order of oxidizing power. Okay, now I personally always use the decreasing oxidizing power table, but unfortunately, in the 2022 to 2024 syllabus, they do not provide you in decreasing oxidizing power. So you do not have the convenience of having the most positive E value all the way arranged to the most negative E value. Okay, yeah. So I will presume by now, you should know what does a more positive E value mean and a more negative E value means. Okay, so never mind, it's okay. So whatever we will be doing, we can just arrange ourselves from most positive to the least negative. Okay, so the first part is to show you the data booklet. What is the difference between 2019 to 2021? Versus 2022 to 2024. All right. So for you all who are watching the video and you would like to do your past year question, you actually can use the 2019 to 2021 for your exercise. But in your actual exam or in your trial or mock exam, then the setter, the question, will extract only relevant and perhaps some, other E values for the question itself for you to use. All right. So now, I want to go through by taking you all through some questions from the most basic calculation of Ecell to increasing difficulty. Okay, and every question here, we're going to look at something different here. Now, the first one I want to take from Summer 22, paper 41, all right, question 2e. So I give a very simple one. Okay, now, so first you can see the question gave us, okay, the table that shows the E values, but they gave it in random order. Okay, random order. So you can see that there is no most positive E value to the most negative E value. So it's okay. What I did was I've conveniently arranged everything from the most positive. Please look at the pink color table. I arranged from the most positive on top, positive 1.67, and decreasing all the way to the negative 1.18 section. Okay, all in decreasing oxidizing power. All right, so normally when I will play from most positive to most negative E value. Okay, so that will be easier for us to make a more accurate decision. So the question now is, suggest the formula of the manganese product when Mn2 plus reacts with Cl2. Now, don't use all the values they gave you. You need to pick the correct 2-half equation. So first, you may want to go and circle where are all the Mn2 plus. So I can circle, find one here, I find one here, and I find the chlorine. There's only one chlorine. Okay, so we will be only using the bottom three half value. So chlorine, okay, is more positive, which is positive 1.36. So chlorine will undergo reduction. Okay, now hence, reduction means move right-hand side. Now then, manganese 2 plus ions will undergo oxidation. If you want manganese to undergo oxidation, right, the equation should shift left-hand side. So there's only one correct answer here, which is the positive 1.23 version. This will undergo oxidation because he is less positive. All right, you can't be picking the negative 1.18 because if you were negative 1.18, since chlorine gas already undergo reduction, then you pick the manganese at negative 1.18. So are you trying to say that, you want to undergo oxidation like this to question mark? No, right? Okay, you either shift right in the negative 1.18 or you shift left, which is an impossible case. All right, so if you only can shift right, which is reduction, then that is not what we want because chlorine already undergo reduction. Hence, your manganese must undergo oxidation. Okay, so circle what you need. Okay, and then therefore we know that this is the half reduction potential for the chlorine and the positive 1.23 is the half oxidation. So we can see these two will be reacting this way. Okay, it will react this way. So what is the formula of the manganese species form? So manganese will form MnO2. All right, type of reaction. Type of reaction, redox. Manganese 2 plus and chlorine will undergo redox. Now, I add one simple question here. Calculate the Ecell, because this is what we're going to talk about today. Now, the calculation of Ecell, the formula, okay, there are many ways to define the formula. The more positive E value minus the less positive E value. Okay, so or it can also go by the reduction cell minus the oxidation cell also can. So the more positive, all right, over here is positive 1.36. The least positive between the two is positive 1.23. Hence, your E cell will be 0.13. Okay, volts like this. Okay, 0.13. So all you can go by the one that undergo reduction minus the one that undergo oxidation. Okay, so this is kind of easy, straightforward. So what is the lesson that you're trying to learn here is you want to align from the most positive to the least positive. Then you can see clearly, because otherwise when they arrange randomly, it's very difficult for us to go and pick the correct manganese ions. Okay, so that is the first and the most simple example. Now, I'm going to move through another example here. Okay, now, the half equation for the reduction of iodide ion is shown. They gave half. They never say undergo oxidation or reduction yet. Okay, use data from the data booklet to predict whether a reaction is feasible when aqueous solution of acidified iodide ions and bromide ions are mixed. Now, first, they only gave the half equation for iodide 5. And now they want you to determine, all right, whether bromide ions and the iodide is feasible. Now, first, we shall go to the data booklet. Okay. Now, you can go and find where is bromine and bromide. There's only one, which is here, which is at 1.07. Okay, so we're going to extract information and we're going to put it here. Okay, so I'm going to list the bromine receiving 2 electrons to give 2 bromide and positive 1.07. I arrange from the most positive on top to the least positive below. Now, so between these two, iodide ions is more positive in the E value. They will undergo reduction. So I will circle my iodate. It will undergo reduction to form iodine. Hence, read the question, bromide ions, not bromine. Circle bromide ions, and then bromide is having a more negative E value. Hence, he will undergo oxidation. So if iodate, more positive, chose the reduction, bromide must choose the oxidation. You have to ask yourself now, in this equation, can bromide undergo oxidation like this? The answer is yes. Okay, it's not like just not the manganese. You have to shift left with nothing in the air. Okay, this one bromide can only undergo oxidation. So therefore, you see a relationship like this. Okay, now, so this is called a feasible reaction. So you're supposed to predict whether feasible or not, am I right? So how do we predict feasible? You have to calculate Ecell. All right, so you want to answer in terms of Ecell, give them a number to prove. So the Ecell is the more positive E value minus the less positive E value. So let me calculate this out. So this will be 0.12. It's a positive 0.12 volts. All right. Now, since Ecell is positive, I minus 3, which is the iodate 5 ions, and bromide ions, not bromine, bromides are feasible or is feasible, the reaction. So when you want to prove feasibility, you want to prove that Ecell is positive. If Ecell calculate out negative, it means that it is not feasible. Okay, but of course, the better version of proving feasible or not feasible, it will be your Gibbs free energy. Okay, now let's move on to another example here. Okay, now, so let's look at winter 20. All right, the halogens chlorine, bromine, iodine differ in their strength as oxidizing agent. These strengths are indicated by the E values for this halogen. All right, so we go to data booklet. Okay, I extracted out the fluorine, chlorine, bromine, okay, and iodine out. So where shall we put our attention to? As you can see here, you wanted the chlorine. Okay, so pen, right? So chlorine, bromine, and iodine, not chloride, bromide, iodine. Okay, be very careful. So then give the E values for chlorine, bromine, iodine acting as an oxidizing agent. The equations are writing in reduction format, right? So reduction means you're an oxidizing agent. So give the value, so you want to quote the values out for them. So chlorine is positive 1.36. Bromine is positive 1.07, and iodine is positive 0.54. So the more positive the E value, the more it will undergo oxidation. Oh, sorry, the more positive the E value, the more they are a better oxidizing agent. That means they will undergo reduction. Oxidizing agent means they will oxidize the other compound. They themselves undergo reduction, isn't it? Okay, so they are arranged in decreasing oxidizing strength. Now, part 2. Deduce which of chlorine, bromine, and iodine will react with a solution of SN2 plus, tin 2 ions under standard condition. So I also went and extract everything got to do with tin 2 plus, okay, and I arrange it from most positive to less positive. So you can see here the numbers are from positive 2.87 all the way to negative 0.14. So I see one tin 2 plus on the right hand side here. I see another tin 2 plus on the left hand side here. Okay, so which, okay, of the 3 halogens will react with tin 2 plus? Halogens are on the left on the equation. Okay, so everybody, so first, okay, the halogens, be any halogen you pick, right? There's a line between here. There's a line. Okay, all the halogen you pick are more positive. Correct or not? So that means one of the 3 halogen will undergo reduction regardless who you pick. Okay, but of course, we know the more positive one will undergo the reduction. So hence, definitely, chlorine will undergo reduction. Now, if chlorine will undergo reduction, the first part on top of the red line has been settled. That means tin 2 plus must undergo oxidation. Okay, now which tin ions will you pick after we did the first example? Would you pick the 0.15 version to undergo oxidation, or will you pick the negative 0.14 to undergo oxidation? All right, we will pick the 0.15. Okay, chlorine more positive will undergo reduction. Tin 2 here, tin 2 undergo oxidation to become tin 4. For those who pick the negative 0.14, your finger is pointing at this position here. So if tin 2 plus in the equation here, you either shift right, which is reduction, not what we want, or you shift left to nothing. Okay, so there's only one answer, which is the positive 0.15 version. Okay, so deduce which of the halogen. So I will say chlorine and include relevant equation. Okay, so you know your half equation, right? So I'll do this one very quickly. I'm going to write the balance equation here. This is the balance equation. Okay, and you want to calculate your Ecell. Okay, I know it's not needed, but let's practice. Okay, we are using positive 1.36 and positive 0.15. So you take the more positive number minus the less positive number. Therefore, Ecell calculate is positive 1.21 voltage. So since it is a positive Ecell, we know that chlorine and tin 2 plus ion is a feasible reaction. But you are required to the word explain between the three halogen who will react. So I say chlorine will react with tin 2 plus because E values of the Br2, Br minus and the E value for I2, I minus, okay, is less positive than chlorine, chloride E value. That's it. Okay, yep. Now, number 3, an excess of chlorine is added to a solution of Mn2 plus. Understand the condition. Give the formula of the product of this reaction that contains manganese. Excess chlorine. You have to be careful with the word excess. Okay. Now, so I'm going to bring this thing up a little bit. Same thing. I went to data booklet. I extracted out everything. Arranged from most positive, as you can see, positive 1.67, all the way to the most negative, negative 1.18. Okay. Pick everything they got to do with the manganese element. Just pick out everything because manganese is a transition element that can exist in variable oxidation state. Okay, perhaps you may undergo, multiple redox. So we will just pick everything got to do with Mn out first. And chlorine, only one equation. Okay, so you can see there's so many Mn related equation out. Okay, but never mind. So first, give the formula of the product of this reaction that contains manganese. Now, they already lock you down by saying they want Mn2 plus. So I'm going to circle all my Mn2 plus. Wherever got Mn2 plus, I will circle. All right. And then they said chlorine. That means is chlorine gas. And they said excess. Okay. Now then, give the formula of the product of this reaction that contains manganese. Okay. Now, chlorine is definitely one of the two of the reactant. So if chlorine, okay, now chlorine, you have to decide what chlorine role should be. Will chlorine undergo oxidation or reduction? So since chlorine is a confirmed reactant, chlorine can only shift right because chlorine cannot shift left to nothing. If chlorine can only shift right, which is reduction, okay, which is reduction. That means the manganese ion must be undergoing oxidation. Therefore, the E value must be less positive than the positive 1.36, correct? So you cannot pick these two because the two E values is actually more positive than your chlorine to chloride ions, 1.36. So now between 1.23 and negative 1.18, which manganese 2 plus would you pick to react with the chlorine? Since chlorine undergo reduction, your manganese must undergo oxidation. Have you have an answer? Okay, so the manganese that is undergoing oxidation is the positive 1.23. Okay, I repeat again. If you pick this manganese at positive 1.23, you can shift left to undergo oxidation. Okay, if you pick the negative 1.18 for oxidation, then you have to shift left to nothing. Correct or not? You only can shift right in this equation, which is reduction for the negative 1.18 version. Correct? So if you want manganese to undergo oxidation, therefore you can only pick the 1.23 version. All right? So therefore, give the formula of the product that contains manganese. So Mn2 plus will form MnO2, which is the product at 1.23 after undergoing oxidation. Okay, so by now you know how to calculate Ecell, how to know which will undergo oxidation, which will undergo reduction. Okay, now next. Let's play with medium difficulty now. Just now was easy, the first three. Okay, now, so let's look at the March 21, question 3. The decomposition of hydrogen peroxide is catalyzed by iodide 5. Okay, and they conveniently arrange from the most positive to the most negative number, and that's nice. Okay, so the H2O2 reduce the acidified iodide. Okay, they will reduce as shown. So they give the balance equation here. So what we can see here is that iodide 5, okay, which are right now, iodide 5 here, the oxidation number of iodine inside here is +5, this is 0. So we know that iodine in the iodide undergo reduction. Okay, and the hydrogen peroxide, this is -1, this is 0, this is -2. Okay, now, so we can see that this is not disproportionation in a way, because you have to split it up, okay? You have to split it up. Now, -1 to 0, and then -1 to maybe -2, we have to decide. So, but since, at a glance, since iodine is undergoing reduction, right, that means your oxygen must undergo oxidation. So looks like it's going to be like this at a glance, very quickly. But it's okay, we can continue first. All right, now, use the data to show that the separate reactions of H2O2 with IO3 minus and with iodine are both feasible under standard condition. Okay, in your answer, give the equation for the reaction of H2O2 with iodine. Right, so first, give the equation for H2O2 with iodine. So you want H2O2 with iodine, right? I circle H2O2 in the most positive to most negative arrangement, and iodine. I also see another H2O2 here. So I already circle all the H2O2 and iodine. Okay, now, so if you have done 3 examples with me, you should know that when you pick 2 equations out, definitely you have to start on opposite end. Okay, now, H2O2, the positive 1.77 is the most positive. Therefore, will undergo reduction. And you check the equation. Can the H2O2 undergo reduction by shifting right? The answer is yes. Because you cannot pick the H2O2 at the 1.77 to undergo oxidation. Oxidation means you want to shift left, which is nothing. Okay, so if you were to pick the 1.77, right, there's only one way out, which is reduction. Okay, now, then if you pick H2O2 at 1.77 to undergo reduction, that means iodine will undergo oxidation. Then you ask yourself, iodine, there's only one here. can they undergo oxidation? Yes, to the left-hand side. Okay, to the left-hand side. So therefore, since the E value is also less positive than the 1.77, so your iodine will undergo oxidation. Okay, now I would like to address if some of you are asking, Miss, can I, cite, Miss, can I choose these two? Okay, can I pick the H2O2 and the iodine at the 1.19 and 0.68? Okay, so it is still iodine and H2O2, right? But can I pick these two? Let's check whether can or not. Now, knowing that 1.19 is more positive, a more positive E value should undergo reduction. You look at your equation, your iodine here, can it undergo reduction by shifting right to thin air? No, the only thing your iodine can do is to shift left by donating 5 electrons. So since your oxidation part, all right, is needed for iodine to shift left, and that is the only way you can shift, hence, you cannot be selecting the so-called 1.19 and 0.68. Now, then you see, let's go to the 0.68 version now. The 0.68 H2O2 over here, okay, they are more negative in comparison to 1.19 in comparison, okay? So the 0.68 will actually undergo oxidation over here. My pen, okay. So if you pick the H2O2, knowing that 0.68 is more negative, he will undergo oxidation, right? Now, oxidation, H2O2 it will shift left to give oxygen here, can. So this H2O2 can undergo oxidation. But the issue here is your iodine have to undergo reduction to shift right to thin air, which is impossible. So you cannot be having iodine on the right hand side, shift left to oxidation. You cannot also be having hydrogen peroxide, shift left for oxidation, cannot. Okay, so I was just addressing, just in case some of you have this in mind. So what we can see, the first combination is the 1.77 and the 1.19. So I would like to highlight these two first. Okay, so first I'm going to calculate the Ecell. The more positive minus the less positive, 1.77 minus 1.19. This would be positive 0.58. A positive means the hydrogen peroxide and the iodine is feasible. Okay, so we need to construct equation to show, correct or not? So since this has 2 electrons and this has 5 electrons, what we want to do is we want to multiply with the coefficient of the other equation. So I quickly answer here. The whole equation on top, I times 5. The bottom equation here, I times 2. The reason of doing that is to make the number of electrons as 10. So I can cut 10 for the reduction and oxidation is 10. Okay? So this is the balance equation. You can simplify this to this version. So after balancing and simplifying it, I will land with something like this. Okay, so this is the first redox between hydrogen peroxide and iodine. The question says reaction between hydrogen peroxide and iodine, and I already answered. Okay, now then, this equation is not the question on top, the equation. So you can see here, on top, hydrogen peroxide reacts with iodine. But currently now, we are actually reacting hydrogen peroxide with iodine. So let me take my cursor and direct you. Whatever we've just done is hydrogen peroxide and iodine. The questions want hydrogen peroxide and iodine. Correct or not? Now, since you already got your iodine out, all right, forming the iodate here. You already have the iodate, correct or not? Okay, now we're going to continue the reaction, okay? Right, so now the second part of the redox, all right, is to use the hydrogen peroxide, okay, reacting with the iodate that is being formed. Okay, now I want you to see the highlighter here. I use a different color. Can you see from your first redox, you already form iodate? You already have this, right? Okay, now then you have hydrogen peroxide since the starting of the experiment here, correct? Okay, so now thanks to your first redox, you already form the iodate ion. Okay, now then go and find your hydrogen peroxide here and here. Okay, so now you want to basically look at all the purple highlighter, which is actually all the circle, what I do. Okay, so if you want to look at so-called circle, right, can. Okay, so maybe I just take away all this. I'll go by circle wise. Okay, so I'll just use a purple color pen. Now you have iodate ions because initially, you know, iodate and hydrogen peroxide here. Okay, you have this, okay. So why did I initially started with H2O2 and iodine? Let's read the question again. Give the equation for the reaction of H2O2 with I2. So that's why I start to circle all the iodine and H2O2. But since the first redox, the final product come out is IO3 minus, right? So now I got IO3 minus in the game. Okay, now then I can use the product from the first redox, which is IO3 minus, and react with the H2O2 that is being formed here. Okay, so the second set of redox, okay, would be these two, where positive 1.19 will undergo reduction and the positive 0.68 will undergo oxidation. Okay, if you're asking me why, or asking yourself, why can't we pick these two? Okay, you cannot pick these two is because H2O2 here is more positive on top. More positive means undergo reduction. Can he shift right? Yes, he can. But if you shift right to undergo reduction, that means you're trying to tell yourself that the iodate must undergo oxidation. Why? Because 1.19 is less positive. That means you're trying to say iodate has to shift left to thin air. Cannot, right? Okay, so that's why it cannot be the first two equation. It have to be the second and the third equation. Okay, so now let's construct a balanced equation. Okay, now 5 and 2, same thing. This equation I need to times 2. This equation I need to times 5. Okay, so six H2O plus 5 oxygen plus 10 H plus. Okay, this is after cutting away the 10 electrons. Now, Ecell value, the more positive 1.19 minus the less positive 0.68. The second set, 0.51. So Ecell is positive means the two equation that I pick is feasible. Okay, can we simplify the equation? 12 and 10 here left 2. Okay. Yep. Okay, that is simplified here. Okay, now so we have two sets of redox here. Now then, write the overall equation for the decomposition of H2O2 catalyzed by IO3 minus. Okay, so what we can do here is I need you to add the equation 1, which is the blue color. Okay, equation 1 plus equation 2 here. Okay, equation 1 plus equation 2. So if you were to add up everything, okay, This iodine and this iodine can cut. 2iO3 minus and 2iO3 minus can cut. Correct? Now, these 2H plus and these 2H plus can cut. All right. So let me see what is the final one. 5H2O2 plus another 5, which is 10, to give let me have a look. 10H2O2, no more in here. 10H2O2 to give 10H2O plus 5O2. Correct? Now, can we check whether is this equation even balanced? 20 hydrogen on the left, 20 hydrogen on the left, 20 oxygen on the left, 10 here, 10 there. Okay, balance. All right. So this is the overall equation for the decomposition of hydrogen peroxide catalyzed by the acidified iodate. Now, personally, this is a little bit challenging, a little bit, but not the most. Okay. Reason is why it is not the most difficult yet is because they actually give you guidance here by telling you use hydrogen to react with iodine first. Okay, because if we were to put all our circle on the table, okay, then you will be circling 4 things. 1, 2, 3, and 4. Then students have to start deciding, all right, would hydrogen peroxide react with iodine first, or hydrogen peroxide react with iodine first? Okay, so because they already guided that please take hydrogen peroxide to react with iodine first, so that's how the blue color pen comes in first. Okay, so it's quite guided in a way, but it's not like overly difficult. Okay, but thought that this would be good to also show you all right, on how you should play with multiple redox, but a little bit more simple one like this. Okay, all right. Okay, the next example, we shall be looking at summer 20, paper 41, question 9. All right, similar to the previous past year that we did. All right, let's try another one here. This one involved 2 redox. All right, as you can see in the question given equation 1 and equation 2. Let's read the question together. Manganese oxide catalyzes the decomposition of hydrogen peroxide as shown. So you can see that the manganese oxide is the catalyst on the arrow. The mechanism involved the formation of the intermediate species Mn2 plus in the first step, which is subsequently used up in the second step. So just in case if your past year asks you, define intermediate. So intermediate is a species that is formed in the first step and is subsequently used in the second step. Okay, now state and use relevant electrode potential to construct 2 equations to show how MnO2 can catalyze this reaction. Okay, so this does not occur in a one redox. Okay, it occurs in 2 redox over here. So first, you need to refer to your data booklet, okay, and arrange everything from most positive to least positive. So for example, if just in case you cannot see, all right, now I have taken and extracted anything got to do with manganese because it's a transition metal. So anything got to do with Mn, you just take it out first, and hydrogen peroxide. Now, so once you have extracted everything, align from most positive to least positive. Okay, now, and then we want to circle hydrogen peroxide. Okay, and pen. Okay, so we want to highlight and circle all the hydrogen peroxide. I see one H2O2 here. I see another H2O2 down here. Okay, now then, the other one will be MnO2. All right, because at time 0, you only have hydrogen peroxide and your catalyst, which is MnO2 here. Is there anywhere else we have MnO2 here? Okay, these 2 positions. right? We have two positions of MnO2. Okay, now first, they say hydrogen peroxide reacts with MnO2 to form Mn2 plus. Okay, they say that you need to form the intermediate species Mn2 plus. Now, what you can see here is that there are two possibilities. Hydrogen peroxide at 1.77 can undergo reduction. MnO2, which is a catalyst, can be oxidized because it's being less positive, but he gave MnO4, which is not what we want. Okay, it's a feasible reaction between 1.77 and 1.67, but it's not giving us the Mn2 plus what we want, because if you use 1.77 and 1.67, then your product form is MnO4 minus, which is manganate. Okay, if you look at the second possibility, MnO2 here at 1.23 react with hydrogen peroxide. MnO2 is more positive, will undergo reduction to form your intermediate Mn2 plus. This is what we want. And your H2O2 being less positive, it will be oxidized to give oxygen gas, which is using a 0.68 E value. So if we were to pick this set of data, then yes, this will be giving us the intermediate. Okay, so you have to pick one H2O2 and one MnO2. So you either pick the top part set A or you pick set B. Now set A is not correct, so we know that this is set B. All right, so we will construct the equation first. All right, so I will take the equation since it's 2 electrons each, right? So what we're going to do is we're going to calculate the Ecell first. So the Ecell, okay, would be the more positive one, 1.23 minus the less positive. So the Ecell calculated will be positive 0.55. Okay, now, and then we want to construct an equation for the 1.23 and negative 0.68. Okay, so the balance equation would be this. MnO2 plus 4H plus. Okay, and then plus H2O2. Okay, to give MnO2, Mn2 plus 2H2O plus O2 plus 2H plus. Now I'm going to simplify these 2H plus and these 4. I'm going to make it to 2 on the left. So I will just make it a bit more clean. I'll just immediately put here as 2H plus. Okay, that's the net effect, 2H plus. Like this. Okay, 2H plus. All right. Now, then I think we're good so far. Okay. Now, that is the first redox equation. Let me just make it a bit nicer. Okay, so that's the first one. Now then, since your intermediate is Mn2 plus, they already say that you need to subsequently use in the second step. So now we want to go and find all the Mn2 plus. Okay, so let me just change. You want to go and find all the Mn2 plus now. Okay, Mn2 plus, Mn2 plus, Mn2 plus. We will just circle all the Mn2 plus in the most positive to most negative arrangement in the table. Okay, now then, when we circle the Mn2 plus here, okay, remember, MnO2 is a catalyst. What is a catalyst? Catalyst is not consumed in a chemical reaction. All right, so you need to pick the Mn2 plus equation that will regenerate out the MnO2 catalyst back for you. So among all the equation, let's look at 1.52 over here. 1.52 Mn2 plus, but it gave manganate. That's not what we want. 1.49 Mn2 plus, Mn3 plus, not what we want. What about this? 1.23. I think 1.23 should be the answer, because if we pick manganese from the 1.23 version, you can obtain back your catalyst, which is MnO2, by undergoing oxidation. So 1.23 is fine. Okay, let's look at the bottom one. Mn2 plus. If we choose this Mn2 plus, then you will form manganese solid. No, that's not what we want. So the correct equation is still at 1.23. So this is what we want. Okay, so now your focus should be on the manganese, okay, 2 plus ion, and I would like to delete all the purple color one. So we only use the manganese 2 plus ions on the right-hand side, which is 1.23. Now, knowing that your manganese 2 plus have to regenerate back, have to. So your manganese 2 plus is forced to undergo oxidation here for the sake of regenerating out the catalyst MnO2 back. So therefore, somebody needs to undergo reduction. So who can undergo reduction when he meets with Mn2 plus at 1.23? The answer would be this one, H2O2 on top. So the H2O2 will undergo a redox, okay, with the intermediate Mn2 plus here, because 1.77 is more positive. H2O2 will undergo reduction, whereas 1.23 will undergo oxidation. Okay, so we can see that there's 2 electrons involved in 1.77 and 2 electrons involved in 1.23. So you can just cut the 2 electrons out in the balance equation. So for the second equation, right, let's calculate the Ecell. So Ecell equals to the more positive, which is 1.77, minus the less positive 1.23. So the Ecell obtained here would be, calculator, give me a moment, 0.54. So it's a positive 0.54. Okay, like this. So it's a positive Ecell indicating that the hydrogen peroxide and the manganese 2 plus ion that we chose is feasible because it's positive. All right. So how can we construct the second equation? We will start constructing the equation something like this. H2O2 plus 2H plus. This is the intermediate that we use. Mn2 plus 2H2O. Okay, to give 2H2O plus MnO2 plus 4H plus. Like this. So I can simplify by cancelling the 2H2O. And this 2H plus, I can cancel off to make it 2H plus here on the right-hand side. Okay, so we have answered the question already. Now, just in case, if you want to add equation 1 plus equation 2 to show the balance equation on top, which is the hydrogen peroxide to give H2O and O2, you can actually. Okay, now, so what you do is you just add your first equation to the second equation. Okay, now, these 2H plus and these 2H plus can cut. All right, and then your manganese 2 plus is the intermediate. It was formed, but it was utilized in the subsequent step. Okay, and then MnO2 is the catalyst. You use it in equation 1, but you regenerate out in equation 2. So what is left remaining would be 2H2O2, okay, to give 2H2O and oxygen gas. There you go. So this is the balance equation given in the question, but it was catalyzed by the MnO2 solid catalyst. It's a heterogeneous catalysis. Okay, so I hope by now you know how to select the correct equation when it involves multiple steps. All right, a multiple version.